Hello everybody, my name is Dongwon Lee from Seoul National University. I'm going to present our new framework for optimizing homomorphic evaluation circuits. This work is co-worked with Usok Lee, Hakju Oh, and Gwanggeun Lee. Homomorphic evaluation (HE) is a perfect solution for privacy-preserving secure computation because it allows for any kind of computation on encrypted data. This enables the outsourcing of private data storage or processing. First, a user encrypts their private data and transfers it to the third party. The third party performs homomorphic computation on encrypted data and gets encrypted results. Then, the third party transfers the result to the user, and he or she can decrypt it and get the desired result. Although HE is a perfect solution for secure computation, building HE applications has been challenging. The following 5 steps, which requires a great deal of expertise, are necessary to build HE applications. Even though the developer is an expert for HE, following these steps is quite complicated. Additionally, it is difficult to manually optimize the HE applications for the best performance, which results in suboptimal outcomes. To deal with these problems, the homomorphic compiler aims to lower the hurdle for non-experts to build HE applications. HE developers don't need to do all of the works anymore. Instead, the homomorphic compiler generates HE applications automatically. However, as they rely on manually developed simple optimization rules, its outcomes are typically suboptimal. In this paper, we present an automatic, aggressive HE optimization framework. We use program synthesis and term rewriting techniques to optimize HE applications. We observed 2 times of speedup on average for 25 realistic HE applications from various domains. Our system learns optimization patterns by program synthesis. An interesting point is that some of these machine-found optimization patterns, like the below example, are so aggressive that we can hardly imagine them for human-devised optimization techniques. Then, we apply the learned patterns by term rewriting. Semantic preservation and termination of the optimizations are guaranteed. Also, we showed the effectiveness of our system in a realistic setting. We were able to optimize 19 out of 25 applications from various domains, and were able to observe nearly 4 times of speedup in maximum and 2 times of speedup on average. Our tool is available as an open source. Our system is named Lobster, which means learning to optimize Boolean circuit using synthesis and term rewriting. Lobster consists of the offline learning phase and online optimization phase. In the offline learning phase, we first collect various training programs, and HE compiler frontend translates it into training HE applications. Then, we use the program synthesis technique to learn optimization patterns. In the online optimization phase, for new input program that is translated by HE compiler, we use term rewriting to apply learned optimization patterns. From now on, I'll explain the detailed process about how we learn optimization patterns and apply them to new HE applications. Let me introduce a simple HE scheme first. For homomorphic evaluation, it is essential to design special encryption and decryption function that allows computation on encrypted data. On this HE scheme, P is an integer as a secret key, and Q is a random integer, and R is a random noise for security that is much smaller than P. Then we can define encryption and decryption function as follows. Based on approximate common divisor problem, it is very hard to find P from encrypted data. When we encrypt and then decrypt the message mu through modular P and modular 2 operator, we get original data mu. Similarly, when we decrypt the addition of ciphertexts underlined mu1 and mu2, we get addition of plain text mu1 and mu2, and it's the same for the case of multiplication. It means that the computation on encrypted data preserves the computation result on original data. We have to note that this scheme can homomorphically evaluate all Boolean circuits. It's because addition and multiplication operator are equal to exclusive OR and AND operator in binary domain. It is well known that we can build all Boolean circuits using exclusive OR and AND gates. In this context, all HE applications are basically Boolean circuits. Until now, it seems quite pretty, but growing noise term during homomorphic operations is a serious performance hurdle to HE. The boxes in the following equations show the noise terms. An important thing is that if the size of the noise term exceeds p, we may get incorrect results after decryption. To prevent this, we should select big enough p so that noise term cannot exceed p during homomorphic operations. Meanwhile, the noise term shows a double increase as a result of addition, quadratic increase as a result of multiplication. So, as homomorphic multiplication repeatedly happens, we have to use bigger and bigger secret key p, which results in the slowdown of HE. This is why multiplicative depth is a decisive performance factor of HE. Multiplicative depth is the maximum number of multiplications from input to output. For example, the blow circuit has multiplicative depth 4. When the multiplicative depth increases, noise increases exponentially, which results in a huge size of P and slowdown of HE. For this reason, to conclude, multiplicative depth is a decisive performance factor of HE. So, now we can define what is HE optimization. HE optimization is finding a new circuit with the same semantics that has smaller multiplicative depth. For example, the below figure shows an example of HE optimization. Because their execution results are the same for all input cases, while the multiplicative depth of the left one is bigger than that of the right one. For HE optimization, program synthesis can be a suitable solution. Program synthesis constructs a program that satisfies a given constraint using given program syntax. If you set the constraint to find the same circuit as the original, and set the syntax that restricts multiplicative depth to be below a certain level, that brings a new circuit with the same semantics as original but with smaller multiplicative depth. In this presentation, I will call this process as optimizing synthesis. But practically, the whole circuit of HE application is too enormous to perform optimizing synthesis at once. In this paper, we present two solutions to deal with this problem. First, we use the localization technique. We first select subpart to focus on and find better circuit using optimizing synthesis. Not the same as before, performing optimizing synthesis for the small subpart is scalable enough. Then we just replace the selected subpart. Repeatedly performing this process, we can optimize the whole circuit step by step. To maximize the scalability of our system, we also learn and utilize successful optimizing synthesis patterns. In the offline learning phase, we first collect synthesis patterns that succeed to reduce the multiplicative depth, and in the online optimization phase, we can reduce the multiplicative depth of the input circuit just by applying the patterns. Now, let's see how we learn optimization patterns. Basically, this process is almost the same with optimizing synthesis via localization. For training HE applications, we first select subpart to focus on and find a better circuit using optimizing synthesis. At this moment, if we succeed to reduce the multiplicative depth, we collect the pair of the circuit as a successful optimization pattern. Then we go on and replace the subpart to the new circuit. We repeat this process until there is no subpart to optimize. In this way, we were able to run 186 optimization patterns. These are some examples of learned patterns. As I mentioned before, we can see that some of these machine-found patterns are quite aggressive. You might be able to see that each of these optimizations are hardly imaginable by human beings. Now, let me introduce how we utilize the learned optimization patterns. Again, this process is almost the same with the offline learning phase. For input HE application, we first select subpart to focus on, but instead of performing optimizing synthesis, we apply the learned optimization patterns, and we replace the subpart into the new circuit. We repeat this process until there is no subpart to optimize. Then, how can you apply the learned optimization patterns? Simply, we can match the pattern with the new input circuit synthetically. However, we cannot flexibly apply optimization patterns in this way. For example, we can find some similar subparts of two circuits, but it fails to match them synthetically. To deal with this limit, we use equational term rewriting that consists of normalization and equational matching. First, we normalize the optimization patterns. We find the same subparts from the patterns, and we replace them with a Boolean variable. From now on, I will name these circuits as old, new, and target circuit. Now, we can find the optimized version of the target circuit by matching the old circuit and the target circuit. Based on equational matching theory, we can find the substitution sigma that can transform the old circuit into the target circuit. We can match a Boolean variable n1 with d1 and d2, c4 with d3 exclusive or t4, and c5 with d5. Then, we apply the same substitution sigma to the new circuit and get the optimized version of target circuit. Based on the equational matching theory, it is guaranteed that the optimized version of target circuit has the same semantics with the original version of the target circuit. Also, we can find out the optimized target circuit has one less multiplicative depth. In this way, our system can flexibly apply the learned optimization patterns to find better circuits. Now, let me introduce the Lobster Performance in a realistic setting. Our benchmarks comprise 25 HE algorithms from 4 sources. Singulata is an open-source homomorphic compiler. It provides 2 HE-friendly algorithms that work for medical purpose and sorting. Sorting benchmarks comprise 4 privacy-preserving sorting algorithms. Hacker's Delight benchmarks comprise 12 homomorphic bitwise operations adapted from Hacker's Delight, which is a collection of bit-twiddling hacks. EPFL benchmarks comprise 7 algorithms designed to test the ability of Circuit Optimizer. We evaluated Lobster on these 4 kinds of benchmarks and compared it to the baseline optimizer. Karpov et al. Is the state-of-the-art HE optimizer based on handwritten optimization rules. Lobster significantly outperforms the baseline in terms of success rate, speed up, and depth reduction. In detail, Lobster successfully optimized 19 out of 25 benchmarks and achieved nearly 4 times of speedup in maximum, 2 times of speedup on average. Also, Lobster reduced multiplicative depth by 22% on average. These results show that machine-found optimization rules can work better than handwritten rules. We also evaluated the effectiveness of reusing learned optimization patterns. We used Offline Runner as an on-the-fly synthesis-based HE optimizer and compared it to the Lobster. It was able to optimize only certain benchmarks and was able to reduce multiplicative depth only by 10%. This shows that reusing the learned optimization patterns improves the scalability of Lobster. Finally, We evaluated the effectiveness of equational term rewriting that is used to flexibly apply learned optimization patterns. We compared syntactic matching to equational term rewriting method. Using syntactic matching only, we were able to optimize only 9 benchmarks and was able to reduce multiplicative depth less than equational term rewriting version. This shows that equational term rewriting allows to flexibly apply the learned optimization patterns. If you are interested in more details, please refer to our paper. Thank you for listening and have a nice day.